Hi everyone, today we're trying to answer a $5,000 question. Can we perform a pre-compliance far-field radiated emission test in our workspace? Well, to answer that question, first let us ask, why do we need to send our unit to the chamber for far-field radiated emission tests? Well, there must be a good reason for that. In fact, it is almost impossible to perform radiated emission tests in a typical normal working environment compared to test the unit in the chamber. There are mainly two reasons. First, as I explained before in the conducting emission test, there are so many equipment in this working environment. Some of them are in standby mode, some of them are working, and they inevitably produce radiated fields. So as a result, this ambient noise has a much higher noise floor compared to chamber. And the second reason is, as you can see here, this is my working environment. I have many metal or quasi-metal structures nearby, and the problem with metal structure is that they can bounce or reflect radiated energy, and sometimes this reflection can cause inaccuracy up to 20 dB. So really, if you cannot control all these factors, there's really no point to perform a far-field emission measurement in your workspace. But then you might be asking, why are we talking about this? Well, if you are design engineers, you will probably have more than 3 or 5 iterations before the final design is confirmed. So for each iteration, you might want to check the conductive emission and also the radiated emissions. And sending this design to a chamber costs money and time and your human resource. So it is a good idea if you can set up a pre-compliance far-field measurement in your lab that will make troubleshooting and iteration much more efficient. So that's the reason we need to discuss this topic. So today we're going to discuss a hybrid method in which we'll use a combined temp cell and far-field antenna to introduce you a method that you can use to get as close as possible to a radiated emission test in the lab. So follow us through. To perform a pre-compliance radiated emission test, as we mentioned, we're going to use a hybrid method. The first step I often do is to test the DUT in the tent, inside the tent, using a temp cell. So I'm going to put the DUT inside the temp cell and then close the tent and perform a scan. The benefits of doing this is to give you a benchmark, because we know what is inside the temp cell is really quiet. So whatever spectrum or spurious results you get from the results, you know it is the true EMI coming from the DUT. You might ask, can we relate that results to the far-field measurement? And the answer actually is no. You might read some articles talking about correlation methods to basically using the temp cell results to predict the far field. But the truth is, it is often impossible to do that. However, the benefit, as I mentioned before, is to know the true EMI performance of your unit, even though it is a near-field measurement. But the information is important, as you will see later. You can see the first demonstration unit is this one. It is a development board with screens and program board, and together with some ribbon cable connection. So this will be our second unit for demonstration. This is an active clamp flyback converter. You will see this board actually uses GaN device, GaN transistors for the power conversion. So we're going to test the EMI performance of GaN devices, which is, some people are really interested to see. In this case, as you can see, we will be using a real-time spectrum analyzer. Now, depending on your DUT size, you should, if you can, you should always try 3 orientations of a DUT. All right, so the result is here with the unit on, and we can see definitely lots of narrow band
noise showing here. The limit line actually doesn't mean anything here because it's a far-field limit line. But what we're interested really is to record all these narrowband signals, and then when we perform the far-field measurement using antenna later on, we can then check each individual point to make sure that all the spirits measured here is not going to exceed the limit. Okay, so that's important. For DUT2, we will test actually on this side and possibly on the other side, and maybe even test on this side as well, just to find out the worst case scenario. Okay, but we'll start with this side first. Even these 2 points which possibly touching the limit are wideband signals, not narrowband signals, so a very typical trace of a power converter. Okay, so again, as I mentioned before, we just need to perform a few more scans and to find the worst case scenario, and then we will save the results, and then we'll move on to far field antenna measurement after this. Okay,
now we move to the far field pre-compliance test. As mentioned before, in order to avoid ambient noise and reflections, the best location for far field measurement, except the chamber, is to find an open space. The best is like a roof or the basement in your workspace, or simply like a field, open field. And when we say open field, really, that's what we meant. As you can see, that's what we talk about when we talk about open space. Wide area with no metal structures. So I would take my antenna and portable spectrum analyzer and set it up your unit 3 or 10 meters away and powered by a UPS, and then perform a test. Well, you get the gist. As you can see, I'm standing next to my full-size biconical antenna. Often this type of antenna has a frequency range between 30 megahertz all the way to 350 or 400 megahertz. And in this frequency range, most of the time we will see emissions caused by a unit, but then the radiated field is radiated by cable structure. So often we use biconical antenna to pick up radiated emission between 30 megahertz to 400, 300 megahertz. And from 300 megahertz up all the way up to gigahertz region, we need different types of antennas. So for example, here, as you can see on the shelf, we have a home type antenna, which is capable from 1 gigahertz to all the way to 6 gigahertz. The log periodic, often from 400 megahertz to 1.2 gigahertz. And we also got some rod antenna and small biconic antenna there. Okay, here we are. We have the test set up in the back garden, simply because here is relatively quiet electromagnetic wise and less metallic objects here. And as you can see, we have a ground plane, we have the listen connected to the ground plane, and the listen is connected to isolation transformer, and our DUT sits on a 80 centimeters tall insulation support, ideally wood, but in this case plastics. We have the mains cable standing around, cable length. You can check the standards, but in this case it's about 1 meter long. And we power the DUT using the mains. And if I measure from this point where my DUT sits, and I measure 3 meters long, and here is my antenna. So this point here to DUT is about 3 meters long. And as you can see, currently the antenna is set as horizontal polarization, but I can also change into vertical, and I can also change the height. So normally I would perform 3 or 4 scans to see which case is the worst case scenario. And in this case, we're only doing the measurements using the full-size biconic antenna, simply because as we checked the EM performance of the DUT in a temp cell, the red flag area where in the frequency range where this DUT radiates the most is often between 30 megahertz to about 300 megahertz. And because it is a power converter, so the main radiated mechanism is actually through the mains cable. So in that case, a full-size biconic antenna often work between 30 megahertz all the way up to about 300 and 400 megahertz is the ideal choice for measuring radiated emission. So in this case, we're going to perform a 3-meter long distance scan, but first we're going to do a ambient scan first, and then we're going to power the unit up and then do the scanning while the unit is powered up, and we're going to compare the performance.
Okay, I want to take a few minutes to explain some of the important things when you perform a radiated emission test using an antenna. And often these are the questions people ask a lot. Now, if you look at the equation showing on top of these slides, you will see that the electric field you measure using an antenna equals the spectral analyzer reading, and with all these other factors here. And you will notice that in this diagram, I have an antenna connect to a small attenuator and then low noise amplifier, and then to the spectral analyzer. But I would like to make it clear that for pre-compliance radiated emission tests in your workspace, you don't need the attenuator and low noise amplifier. People say you need attenuator for better matching, but in my experience, it doesn't really matter. And the reason that people argue about using a low noise to the small size, especially small size antenna, is they say that you can effectively lower the noise floor. But this is only true if you use it in a chamber where the ambient noise floor is very low. Then you can use this method. In your real work environment, when you use a low noise amplifier, you amplify everything, including the noise floor, the local radio transmitters, and the DUT signal. So effectively, it's not really lowering your noise floor. So that is why I would say let's keep things simple and keep things straight, right? So in this case, if we forget about the attenuator, the low noise amplifier, we make things much simpler. So if you look at this, all you need to do is to connect your spectral analyzer to your antenna. Now, quick explanation of the antenna factor. Antenna factor, as you can see, is defined as a factor against your frequency. As your in this case, you can see there's a V-shape antenna factor. The general rule is you wanted the antenna factor as low as possible, but because of the physical build, each antenna has each antenna has its own antenna factor. For small size antenna factor, inevitably in a lower frequency range, you will have higher antenna factor compared to a full size antenna. And when you perform the radiated emission test, simply add the antenna factor in your reading. Okay.
So as we explained, the antenna is connected to the spectral analyzer, where the spectral analyzer actually sits, in this case, in my office. So it's have a fair long distance between the two. And I'm holding a data sheet. As we explained, all antennas, when you buy an antenna, the manufacturer will often supply you with an antenna factor. So in this case, I have the data sheets in my hand, and actually the data sheet provides the antenna factor for 1 meter, 2 meters, and 3 meters. So that's really handy because sometimes, as I said previously, you would like to move the antenna a little bit closer, maybe because the ambient noise is very big. So in that case, say you want to place the antenna at 1 meter distance, you need the antenna factor at 1 meter. So in this case, we are going to use the software to control the scan. The antenna factor can be stored in the software, so I don't have to do anything. I can just click the scan and the software will basically perform the scanning. And we're using real-time spectral analyzer. So first we are going to do an ambient scan, as I said, and then we're going to power the unit up and do a scan with the unit is on. Okay. Power the unit up. Now let's perform another test using set 1 and see what happens.
And then trace 1, set 1 in dark green is the tensile results. Okay, so let's have a look. First, as I said, beyond 300 megahertz, that's really not our concern. So our focus should be really between 30 megahertz and 300 megahertz. This bit which is the far field measurement, could be caused by cable radiation, where tensor cannot see that. Okay, so it tells us that we really need to pay attention to these points.
Let's have a look at the other DUT, the screen and display boards there. Okay, so in this case, now as you can see, we're moving to the office. So compared to outside, it's slightly worse in terms of the ambient. As also you can see, now we changed the antenna. So in this case, we're using a TBM-A1, very small biconic antenna capable from 30 megahertz all the way up to 1 gigahertz. The reason is because we know that board will emit noise from the tensor result pretty much from like 200 megahertz to 1 gigahertz, and it's narrow band. Therefore, as the frequency goes up, when we talk about over 200 megahertz or 100 megahertz, then your antenna effectively can be moved a little bit closer, because we know there is a relationship between the far field and near field, and it often is in a lower frequency range. You need to be aware that you have to keep a good distance to measure the far field. As frequency increases, your distance can be reduced. As you can see here, the small antenna we're pointing to the DUT is actually 2 meters away, okay? And in fact, when we perform the measurement, we will move the antenna to 1 meter away. Then the difference is, when we perform a 3 meter distance test, we can use the 3 meter limit line. But when we perform a 1 meter distance test, we can just basically lift up the limit line by 10 dB. Okay, so now we have a look at the test setup. When you test something in the work environment, as always, we want to minimize ambient noise as much as we can. So as you can see here, we're still using the laptop to control the spectrum analyzer, but the laptop is not powered by the power supply, but rather just keeps the battery to keep the noise, ambient noise down. You can also see that we have 3 ferrites, each have multiple terms on the cable to suppress the noise coming from the spectrum analyzer. Spectrum analyzer is connected to the antenna, and we also have some ferrite on the coaxial cable just to suppress the noise. And in terms of here, we have wooden table, 80 centimeters above the ground plane, and we have a listen. You might ask, why do we need a listen for radiated emission tests? Well, in fact, the listen here is to provide a defined impedance to the mains cable, because if you don't connect the unit to a listen, then chances are you have no idea what is the mains impedance. It could be high impedance, could be low impedance. Regardless, it will affect the RF current flow on the cable. So that's why we always want to provide a listen for the radiated emission test. Okay, so let's have a look at the performance of the DUT at 1 meter distance.
The dark green is the tensor results, and the light green is the sort of antenna measurement, because tensor shows a spike here, spikes here, here, here. So these 4 definitely we need to check. So let me just put back the antenna results. This is a peak scanning result, and we are comparing against a quasi-peak limit, QP line here. So what we'll do is we're gonna actually select a point, and we're gonna perform a quasi-peak later on. But anyway, so if I were to test my product to make sure that it can pass the radiated emission test in the chamber, I will need to bring this down regardless. I need to bring this down to be the level below the margin line to give me good confidence. Okay, even the quasi-peak result is higher than the limit line we defined, definitely a lot higher than the margin line. So I wouldn't be feeling confident to send this unit for chamber testing. So I have a lot of work to do to bring down the noise before I can send it to the chamber. So the step really is now to fix the issue and then basically repeat the same thing again, tensor plus the far field, until we're happy. Okay.
I said for this particular product, which is a power conversion board, the main radiation route is through the cable, right? Through the cable, and that is why sometimes people say you can place an RF current probe on the cable and use the common mode current information to predict far fields. Now, this method actually has two limitations. One is, as we explained, it only applies for certain types of products. For example, if it is a power converter or motor drive board, this often works simply because it's broadband noise and it's the cable radiation that dominates. Second is, this method has its own frequency limitation. It often works from 30 megahertz all the way up to perhaps 300 megahertz or 400 megahertz. Some people argue it can work up to 1 gigahertz, but often, according to my experience, is that from 300 megahertz, it can give over prediction. But regardless, this is a very powerful tool, especially if you don't have a full-size antenna. This method was first introduced many years ago by a few EMC engineers and consultants. Doug Smith has talked about this method in the past, but the person who makes this method perfect is Mr. Andy Eady, based in Canada. He has an excellent article on this, giving all the equations, which are attached to the show notes. You can have a look. So as you can see here, we have an RF current probe. We have the DUT sits on the table, and it's very simple. Basically, I just clip the current probe to the mains wire, and the distance from the current probe to the DUT, there's no rule. But if you place on a different location of a cable, then you will have different results. But in this case, for demonstration purpose, we often just put it on a location about 10 centimeters away from the DUT. And also perform far field measurements using an antenna which sits at 2 meters away, and we're going to compare the 2 meters away far field measurement results against this prediction method, and to see how close the results can be. Okay.
So as we can see here, the red trace is the predicted far field measurements by the RF current probe, whereas the green trace is the far field measurement. Now, as a quick scan, I would say these two results are pretty much similar, especially in the frequency range where is a big concern, which is from 90 megahertz all the way to about 150, 160 megahertz. We definitely have very similar EMI profile. There are limitations. First is the applicable frequency range, and second is depends on your product complexity. In this case, it's a power converter using power electronics devices. So for that particular products, this method is very useful. However, if you develop something like high-speed digital circuits using lots of FPGA, Wi-Fi, Bluetooth modules, then this method is less useful.
If you want to learn more about EMC troubleshooting, testing, or design techniques, I would welcome you to the EMC and Compliance International Trade Show scheduled for May 16th and 17th this year in Newbury Racecourse. You can check all the details on the website. That's the biggest EMC event in the UK, at least. So feel free to join us. Thank you.